Welcome back, guys. In this video, we discuss eigenfunction expansion. We're just going to do a second example of the method that we discussed in the last video. And this is problem 31 in the Solution Techniques for Elementary Partial Differential Equations, second edition by Christian Constanda. It says, consider the regular Sturm-Liouville problem. We've got this differential equation subject to these boundary conditions for x between 0 and 1. And we're told that this problem has these eigenfunctions. F sub n of x is cosine of 2n minus 1 times pi times x over 2. So it looks like we've got odd multiples of pi over 2 multiplying x for n equals 1, 2, 3, and so on. Those are our eigenfunctions. And we're asked to construct the generalized Fourier series expansion for this function. I do want you to notice that this is a piecewise smooth function. So it makes sense to talk about finding a generalized Fourier series expansion, otherwise known as an eigenfunction expansion for this function. But let's look at what u is. It's defined on the interval from 0 to 1. And on the interval from 0 to 1/2, the function value is 1. So I've got that. And on the interval from 1/2 to 1, well, at 1/2, we've got 2 times 1/2 is 1. 1 minus 3 is -2. Trying to make this at least close to scale, probably having a little trouble. So we get -2 there, not there. And then at x equals 1, we have 2 minus 3, which is -1. I'm not using that as my tick mark. I'm using that as my tick mark. And that's clearly a linear function. So what we're going to see is a line segment over here. So this is u of x. Now, when we construct the Fourier series or the generalized Fourier series expansion of the function, we're not actually going to get this back. The series that we construct will converge to this almost on the interval from 0 to 1/2. That function will be equal to 1. But at 1/2, we've got a jump discontinuity. So things are a little different at 1/2. So there's my -1, there's my -2. At 1, we do get -1. And we still have that open circle at x equals 1/2, y equals -2. Now this series that we'll come up with, the sum as n goes from 1 to infinity of c sub n times the f sub n of x, where the f sub n of x are these functions here. That series will converge to this, but it's going to converge to u of x when u of x is continuous, and it's going to converge to the average of these two limits when u of x is not continuous. The average of 1 and -2 just comes from adding 1 and -2 and then dividing by 2. So we get -1/2. Just halfway in between, which makes sense. This is what our series will converge to. Now we just want to find that series. Now the first thing that we need to do in order to find that series is identify that weighting function. So we're going to take our differential, or take our regular Sturm-Liouville problem, and we always want to compare it to the form of a regular Sturm-Liouville problem. So we've got p times f prime prime plus q times f plus lambda times sigma times f equals 0. And then we have two boundary conditions. I'm not going to list those. I'm really just comparing the two differential equations. Now, I think if we compare this, I think we can see immediately that p is just 1 because we've got an f double prime here. If I'm looking for a term that involves my function f times another function not involving lambda, I don't have one. So that tells me that q of x must equal 0. And then that means if p is 1 and q is 0, the weight, that sigma of x is the function multiplying lambda and f. Since I've got a lambda f here, sigma is just 1. And of course, that is positive on the interval from 0 to 1, or it's actually positive all the time. We've got that as our weight, and it satisfies the requirement that that weight is positive on the interval of interest. Okay, so now if we want to find these eigenfunctions, we will start by assuming that u is equal to this. Now we know that it's not going to be exactly equal to u. It's going to be equal to this when we're done. But that's good enough for us. That's what we would do in general. And in this particular case, the f sub n of x are cosine functions. We've got odd multiples of pi over 2 multiplying x there. Then in order to find the c sub n, and that's what we're looking for, we want to multiply this equation that we just stated by sigma of x times f sub m of x. And this time, sigma of x is just 1. F sub m of x looks just like this. We're going to replace the n with an m. Okay, we're going to multiply by that, and then we're going to integrate over the interval of interest. We're interested in the interval from 0 to 1. Okay, so we have on the left u of x times cosine function. On the right, we've got the sum, as n goes from 1 to infinity, of c sub n times cosine of 2n minus 1 times pi x over 2 times another cosine function, cosine of 2m minus 1 times pi x over 2. And then we will integrate all of these from 0 to 1. Now this integral over here is 0 when n is not equal to m. And that allows us to simplify. So this is going to give us on the right c sub m. So there's only one coefficient that's left after all of the others have been multiplied by 0, times the integral from 0 to 1 of the product of two cosine functions, where the angle inside is identical. They're going to be exactly the same. So we're going to have a cosine squared of 2m minus 1 times pi times x, all divided by 2. We're going to integrate that. And again, this comes from the fact that our functions are orthogonal. Your dx. Okay, and then typically what we do from here is we switch from m back to n, and that's just a matter of preference. And then we are trying to get this by itself after switching n back to, or m back to n. It's the interval from, or c sub n is the integral from 0 to 1 of u of x times that cosine function. All divided by the integral from 0 to 1 of this cosine squared function. Okay, so now you just have to evaluate a couple of integrals and substitute, and then you'll have the coefficients, and you just substitute those back into the form of the eigenfunction expansion, and then you've got your eigenfunction expansion for u. It's actually really simple. So let's do the integral in the numerator first. Now remember, u actually had two pieces. It was equal to 1 on the interval from 0 to 1/2. So we're just going to have 1 times cosine of this expression plus u times the cosine on the interval from 1/2 to 1. And on that interval, u is equal to 2x minus 3. Okay. This one is relatively straightforward. The antiderivative of cosine of a constant times x is sine of that constant times x. And then if I'm taking the derivative, I'd have to multiply by that constant. When I take the antiderivative, I have to divide by that constant. Since our constant is a fraction, dividing by that fraction is the same as multiplying by the reciprocal. So we're going to have a 2 over 2n minus 1 times pi out front. We'll evaluate this expression from 0 to 1/2. Then over here on the right, we're going to have to use integration by parts. I recommend using tabular because we'll use, or we'll let u be the polynomial and dv be the cosine function times dx. Take the derivative of u until you get 0. And you're going to take the antiderivative over here until you have the same number of rows in each column. Antiderivative of cosine is sine. And again, since I've got a constant multiplying by the x, I divide by that constant. Since our constant is a fraction, we multiply by the reciprocal. Antiderivative of sine is negative cosine. We're going to multiply by that fraction again. So we're going to end up with a 4 over 2n minus 1 quantity squared times pi squared. I didn't really leave myself enough space to write that out. And then using tabular integration by parts, we'll have u times v. Or minus the integral of v du, but the integral of v du gives us this other result. So we just multiply across this diagonal, multiply by positive 1, and then add, multiply across this diagonal, multiply by negative 1, and add, and then we're done. Negative 2 times that negative 4 is going to give me a positive 8 in that numerator. Of course, we're evaluating both of these expressions over the interval of interest, which is 1/2 to 1 for that second one. Okay, so that is the integral in the numerator. We just have to simplify it a little bit. No problem. So when I substitute in x equals 1/2 here, we're going to end up with 2 over 2n minus 1 times pi times the sine of 2n minus 1 times pi, and then 1/2 is in the numerator, but then we're also dividing by 2. So we could say, instead of having 1/2 in the numerator and then dividing by 2, we could just multiply the entire expression by 1/2. We'd end up with a 4 in that denominator. So it looks like I've got odd multiples of pi over 4 here. And then when x is equal to 0, we're going to have a constant times sine of 0, which is 0. So that piece is gone in that case. And then over here, when x is equal to 1, we get the following. 2 minus 3 is -1. So I have -1 times 2 is going to be a -2 over this 2n minus 1 times pi times sine of 2n minus 1 times pi over 2 minus the expression that we get when x is equal to 1/2. So we'll have 1 minus 3 is -2. -2 times 2 is -4, and we're subtracting that. So we're going to add 4 over 2n minus 1 times pi times sine of 2n minus 1 times pi. And we have a 2 here and a 1/2 there. So that'll be pi over 4 there. Okay, we still have to evaluate this expression involving the cosines. So we'll have this. We'll have 8 over this constant. When x equals 1, we've got cosine of 2n minus 1 times pi over 2. A lot of arithmetic and simplification. Nothing too difficult here. Then we subtract what we get when we evaluate that expression at x equals 1/2. You're going to have odd multiples of pi over 4 inside that cosine function. Okay, so now let's explore a little bit sine and cosine. And we've got odd multiples of pi over 2 inside the sine functions, odd multiples of pi over 2 inside of some of the cofunctions, and then cosine functions, and then some odd multiples of pi over 4. So let's see. As far as sine is concerned, our sine function looks like this. This is y equals just sine of some angle, A. We've got pi over 2 there, pi there, 3 pi over 2, then 2 pi, then 5 pi over 2, and then 3 pi, then 7 pi over 2, and then 4 pi, and so on. So whenever we have this sine of odd multiples of pi over 2, we're talking about sine of pi over 2 and sine of 3 pi over 2 and sine of 5 pi over 2 and sine of 7 pi over 2. Of course, we're talking about odd multiples of pi over 2 where n is positive. So we end up with that first multiple of pi over 2 being pi over 2. So this is actually alternating between -1 and 1. We get 1, -1, 1, -1. So this is -1 to the n. When n is equal to 1, we are at 1, right? And we get 1 here. So actually, I think that should be -1 to the n plus 1. Okay. And then as far as cosine is concerned, at the odd multiples of pi over 2, cosine looks like this. I wish I had drawn my scale identical to the one in the numerator, or not numerator, but the one above it. That's fine. Cosine looks like this. Get cosine of some angle. And at pi over 2, we get 0. And at 3 pi over 2, we get 0. And 5 pi over 2, we get 0. All of the odd multiples of pi over 2 give us 0. So that means, let's see, what did we just say? We said sine of 2n minus 1 times pi over 2 turns out to be -1 to the n plus 1. And cosine of 2n minus 1 times pi over 2. Those are odd multiples of pi over 2, will give us 0. So that means this term is gone. Okay, so let's combine these guys. Like I've got sine, a constant times side of odd multiples of pi over 4, and I have something similar here. I've got 2 of those here and 4 of those there, so it looks like I've got 6 of those total. Then I've got this guy, which alternates, -2 times -1 to the n plus 1 over 2n minus 1 times pi. And then we took care of that, and that. That's 0. And then we've got the cosine term. Okay, and multiplying this -1 to the n plus 1 by another -1 is just going to make that a -1 to the n plus 2, which is the same as -1 to the n, because multiplying by -1 squared doesn't change anything. So I'll just change that to a -1 to the n. Okay, so that is the numerator of this expression. Now we just need to evaluate that expression in the denominator. And you might have a table that tells you what that value is. It's easy enough to use a power reducing formula from calculus 2. So we'll do that. Cosine squared of an angle is 1/2 of 1 plus double that angle. So if I multiply this angle by 2, that 2 will reduce, and I'll have cosine of odd multiples of pi x. All right, so I've got 1/2 times antiderivative of 1 with respect to x is just x, and the antiderivative of cosine is sine. And then I've got a constant multiplying my x out front, so I'm taking an antiderivative rather than multiplying by that, which is what I would do if I was taking a derivative. I divide by that constant. We evaluate from 0 to 1. At 1, we get 1 for x. And this is sine of odd multiples of pi. And then at 0, we get 0 plus constant times sine of 0, which is just 0. Okay, now, but remember, odd multiples of pi, even multiples of pi, any multiple of pi, if at those values, our sine function will be 0. We get 0, or sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, 3 pi, 4 pi. It's always 0 at all of the multiples of pi. So this is 0. And it turns out we just have this one non-zero term. It's 1/2. So that means our C sub n is actually equal to this expression divided by 1/2. I know it's a lot. Dividing by 1/2 is the same as multiplying by 2. So we'll have 12 over 2n minus 1 times pi times this sine function, plus 4 times -1 to the n over this, minus 8 times the 1/2. Let me divide by 1/2. Excuse me, we divide by 1/2, so we're going to multiply by 2, so that'll be a 16. Okay, and those are our coefficients. Ooh, that's a doozy. Now, if you're checking your answer in the back of the book, in the Coach and Constanda textbook, the solution is not always written in exactly the same form. Here, the solution, it looks like someone has factored out the 4 over 2n minus 1 squared pi squared. And then that's what we would have here. We see that we've got a 12, a 4, and a 16. So we could factor out a 4 from all of those numerators. We could also factor out this expression from all the numerators or from all the denominators. Now we don't have that in every denominator, so we'd end up with extra factors of 2n minus 1 times pi for each of these terms. But if you do the simplification, you can see that if I take this and I multiply it by this 4 times 2n minus 1 times pi times sine of these odd multiples of pi over 4, if you actually do that computation, what you get is, actually, I don't get exactly the same term that I have right here. You end up with 16 times sine of 2n minus 1 times pi over 4. And I only have 12 times sine of 2n minus 1 times pi over 4. Okay. Then the next one is going to be the negative 16 times that. It looks a little different than what I have on my paper. It's possible that I made a mistake, but it's also possible that this has just been written in a slightly different form. I chose to reduce, cancel anytime we had something that could be reduced. And we just went straight to the integration by parts over here. So I don't know, maybe this is wrong. I don't think so though. You should check it out and let me know if it's right or if it's wrong. So these are our coefficients and they are quite involved. U of x, well, corresponds to, let's use a little tilde to say it corresponds to this series. It's the sum as n goes from 1 to infinity of this I think the person who wrote the solutions manual probably just simplified to make it a little cleaner, but also take up a little less space with without all these extra factors. Those are our coefficients, and what are they multiplied by? They are multiplied by cosine. Just write it down here, times cosine of 2n minus 1 times pi times x over 2. Now, sometimes students will struggle with this. They'll think, those are constants? Yes, those are constants. There are no x's here. For different values of n, we're going to get numbers out of this. We're going to see odd multiples of pi over 4 here, sine of odd multiples of pi over 4. So that's going to be square root of 2 over 2 and square root of 2 over 2 and negative square root of 2 over 2 and then negative square root of 2 over 2. And then it'll be that there'll be 2 that are positive and then 2 that are negative, and it'll repeat that pattern. Thinking about pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Something similar is happening here with the cosine of odd multiples of pi over 4. We're going to have square root of 2 over 2, then negative square root of 2 over 2, then negative square root of 2 over 2, then positive square root of 2 over 2. So it looks very similar to the pattern that we see for these sine multiples of pi over 4, but the SIGN signs out front are not exactly the same. But those are just numbers. These are numbers. This is a number. This is just an odd number times pi. So those are all our coefficients, and we're going to take those and multiply them by these functions of x. And as we do, if we were to take infinitely many terms here, as n goes from 1 to infinity, we would get something that converges to u of x whenever u of x is continuous, but it converges to the average of the limit from the left and the limit from the right at the jump discontinuity, which occurs at x equals 1/2. So u of x is associated with this on the interval from 0 to 1. And the series on the right converges to this function right here. You could write it down this way. You could say it is equal to 1 when x is between 0 and 1/2. We're going to get negative 1/2 at x equals 1/2. And then we'll have that 2x minus 3 when x is between 1/2 and 1. Now you might want to check those coefficients because it doesn't look like I have exactly the same answer as the answer in the back of the Constanda book. Or maybe I made a mistake in my arithmetic or my my calculus, although I don't think I made a calculus mistake. It's very possible though that I wrote something down incorrectly. Let me know if you catch the mistake and I'll be happy to fix it. Or at least we'll put a note in the description of the video. I hope this helps you understand how to solve these problems. Let's again just talk about what we did. First, we compared this to this so that we could identify that weighting function, which happened to be 1 in this case. Then we said, let's assume that u is equal to this, and then say, okay, if these are equal, what would the coefficients have to be? In order to find those coefficients, we'll multiply by the weight sigma and f sub m of x. We use orthogonality to get rid of most of these, all of them except for 1. And then we solve for that coefficient, and then we choose to switch from m back to n. And we have c sub n is equal to this. Then we evaluate those expressions, which required a little integration by parts, a little, antiderivative of cosine of kx, where k is a constant. Nothing too fancy. We ended up with a lot of terms. It looked pretty bad. We tried to reduce where we could using the fact that sine of odd multiples of pi over 2 alternates between -1 and 1. Cosine of odd multiples of pi over 2 gives us 0. Sine of multiples of pi will be 0 every time. We used all of that to our advantage here to simplify this expression. We still ended up with 3 terms, this plus this plus this. And then we have this over here. Now, again, I will say that the answer in the Constanda textbook, in the back of the book, does not involve sine of odd multiples of pi over 4 and cosine of odd multiples of pi over 4. It talks about sine of odd multiples of pi over 4 and so a corresponding sine function that is related to this cosine function. It's all been written in terms of sine rather than having any cosines in the answer. I have a suspicion, I have a hunch that the reason why my answer doesn't look like theirs is because I've written everything in terms of sine and cosine here, whereas the answer in the book is written in terms of sine with different arguments, just a couple of sine functions there and there with different arguments. But hopefully they're equivalent unless I made a mistake. So this is our answer, and this series converges to this. Almost it converges to that, except for at x equals 1/2. At x equals 1/2, it converges to the average of the limit from the left and the right of the original function.